wanted to talk to you today about a reasonably new science. It's gravitational wave science, but it really is opening up a new way to look at the universe. And so I've entitled the talk A New Window on the Universe. And this opening image that I have up on the top here is actually a mural that's been painted by an incredible artist who works for OzGrav, which is our gravitational wave collaboration. And this mural actually sits on the supercomputer at Swinburne. And so we have a supercomputer that we use to analyze gravitational wave data. I'll talk about what that looks like very shortly. But this beautiful image of Einstein staring out towards two black holes, which are about to merge, really is apt and really does sort of convey a beautiful image of the type of science that we're going to be discussing today. There's a lot of artistic integrity to this, so don't read too much into the accretion disks that are going around the black holes, the jets coming out, everything lined up beautifully. There is a lot of artistic integrity to it, but it really is. It does convey a very nice picture. I can see the chat, so people should feel free if anything I say doesn't make sense. Should absolutely feel free to type questions in the chat or yell out if that's possible, and ask questions. I'm happy to make this as interactive as people would like. So I want to start on a little bit of a journey, and this is a field of science that in some sense is 100 years old, but actually in another sense is only 7 years old. And the first discovery of gravitational waves did only occur 7 years ago. But I don't want to start there. Instead, I want to start around about 1 billion years ago. These are the kinds of timescales we're going to get used to. So this is now 1 billion years ago. Two black holes were orbiting around one another, slowly orbiting around one another. Actually, it looks slow in this image, but it's actually quite quick, and we'll talk about that shortly. And what you can see is the two black holes, as they orbit one another, they're getting closer and closer and closer together. Okay. And you can see that eventually these two black holes just now have merged into a single black hole in what actually looks like a kind of pathetic merger in the end, despite the fact that these are incredibly massive black holes. So I might play that again for a bit of effect. These are incredibly massive black holes. So in fact, one of the black holes, you can see the bigger one, where hopefully you can see my mouse. This bigger one is around about 36 times the mass of our sun. And this smaller one is around about 29 times the mass of our sun. And the reason that they're spiraling in on one another, they're captured in an orbit with each other, but actually they're losing energy from that orbit because they're emitting these gravitational waves. Okay. Now, if I play this one more time, then we'll see right at the end, right at the end, you can see this is two black holes on top of an image of background stars. Now, this is just an artistic impression of what's called a numerical relativity simulation. But you can see the image of the background is really wobbling around quite violently towards the end there. And what this is the gravitational wave signal that is being emitted from these two black holes as they merge. It's distorting the way we see light that comes to our eyes, or in other words, it's distorting that background image. But these gravitational waves get flung off in every direction. They travel at the speed of light until eventually they reach Earth. So that was around about 1 billion years ago. Let's fast forward almost 1 billion years to 1915. This gentleman on the right, this is Albert Einstein. And in 1915, he wrote down what is now known as the general theory of relativity. And the general theory of relativity really tells us how gravity works. Okay, so we had this theory that Newton told us, and it is all about forces between any two objects. And that was all well and good, but it wasn't quite working out. Einstein comes along and solves a lot of outstanding problems associated with this Newtonian gravity. Things like the orbit of Mercury, we couldn't quite explain. And Einstein comes along and he says, I have this new theory, and it actually works by considering space-time, so space and time, as this unified entity. And so what we think of now is not space being separate from our dimension of time, but we think about this one entity and we think about gravity as being a manifestation of geometry of that four-dimensional space-time. Now, this is a really technical concept and it can be quite hard to get your head around, but there's a beautiful phrase that was from John Wheeler some sort of 30 or 40 years later, and it appears in what we call the Bible of this field, which is a book called Gravitation from Misner, Thorne and Wheeler. And you might recognize Thorne, but we'll get back to Kip Thorne soon. And this phrase is that space-time tells matter how to move and matter tells space-time how to curve. And so what we mean by that, if you look at this image on the left, is you can see that there's the sun, and it's sitting there, and the sun is really quite massive. It's got a lot of mass, especially when compared to the Earth. So the sun curves this space-time, which is depicted here as, some two-dimensional curved sheet, just like a trampoline or something like that. In reality, it's a four-dimensional curved object, which is very hard to get your head around. But this two-dimensional analogy is really quite beautiful because the sun curves the sheet. And if I now imagine that I put some object near the sun, it's going to want to move towards the sun simply because it's moving within that curvature of the space-time. Likewise, you can see the Earth here. The Earth is also curving this space-time geometry. And the Earth, if I think about this analogy a little bit more, if I imagine that I'm on a trampoline and I have my sun is sinking this trampoline down, and I put the Earth in there somewhere close and I move it with a velocity that's tangential to where it wants to fall, it's actually just going to orbit around. Okay, so if I don't have any friction, this object is going to orbit around. So you can see that you can construct orbits of, for example, the Earth around the sun, the moon around the Earth, two black holes around one another. You can construct these orbits just as this manifestation of this curved, albeit four-dimensional geometry. Now, take that analogy one step further. As my Earth is sitting on the trampoline and it's moving around the sun, just like when ducks swim along the surface of a pond of water, little ripples of that curvature of the trampoline are going to come out. In that case, they're going to come out at the speed of sound. In the case of our four-dimensional geometry, they're going to come out at the speed of light. And that is these gravitational waves that were predicted by Einstein. In fact, he predicted them in 1916 already, only 1 year after he came up with this new theory of gravity. So we fast forward a little bit. That was 1915, 1916. Einstein predicts these ripples of gravity that should come out at the speed of light. Einstein actually said they're so small that we'll never detect them. We'll never be able to detect them. And I'll quantify what I mean by that very shortly. I'm going to do some maths. I realize. Am I unmuted again? Okay. So I realize people are having dinner and possibly the last thing they want to see is some maths, but I will walk you very carefully through some very simple maths in just a moment. But so we're fast forwarding now to around about the 1980s. And through the 1980s and 1990s, some brilliant physicists and astrophysicists had this idea that we could try and detect these gravitational waves. The story goes back a lot further than that, but I don't want to take you through the whole thing. So they built what's called these gravitational wave interferometers, and that's what's pictured here. So there is a gravitational wave interferometer in Hanford, which is in Washington, up in the northwest of the US. It's on a nuclear reserve, which is why the background here looks, pretty horrible. It's not all that nice a place to visit. And then there's another one, which is some 1,000 kilometers away, down in Livingston, which is in Louisiana. This is a slightly nicer place to visit, although you've got to be careful of the alligators in the swamps. But regardless, what these things are these huge experiments. So you can see that there's a base station right down in the bottom corner here, and there's a 4-kilometer long arm that comes off in one direction. This is a 4-kilometer vacuum tube. And I'll describe in a second what happens within that vacuum tube. But there's a 4-kilometer long vacuum tube going in one direction and another 4-kilometer long vacuum tube going in another direction, exactly perpendicular. So these two things are at 90 degrees to one another. The same at Livingston, 4 kilometers out in one direction, 4 kilometers in another direction. to give you a sense of scale, if we built one in Australia, this is what it would look like. Now, we wouldn't build it in near Uluru. There's no way we'd be able to do native title for that, and nor would we want to. But I will say that towards the end of the talk, I'll talk a little bit about that we do want to build one of these in Australia, and we have very, very good reason for wanting to build one in Australia. So I'll mention that towards the end. Now, we're now going to fast forward to 2015, and in fact, on the 14th of September in 2015. And this is a remarkable day for people involved in this gravitational wave experiments, because it was the first time that we ever detected these gravitational waves. So you'll note that Einstein predicted them in 1916, and we detected them almost 100 years later, in fact, 99 years later, on the 14th of September in 2015. So what I'm showing you here is the data that came off of these two experiments. So if we start on the top left, you can see this is time on the horizontal axis, okay, and what we call strain on the vertical axis. And I'll talk about what this strain is shortly. But just notice that this goes over a period of something like 200 milliseconds. So it's not very long, okay? It's not a very long series of data. This strain number is very small, but we'll get to that. But this is, in my mind, the most beautiful image in all of science, okay? Now, I'm very biased on this, but you know, it is. And let me try and explain why. What you can see here, if we look over to the left of this, this is the data in red that came in the experiment at Hanford in Washington. And you can see on the left here, it's just noise. This is what the data always looks like. It's noisy, it's ugly, it doesn't have any really coherent signal to it. But then what you can see is around about at this 0.35 second mark, which is just an arbitrary number, it's nothing to worry about here. You can see that some structure starts to come out of it. And you can see we start getting these oscillations, and the oscillations grow. So the amplitude of the oscillations gets bigger, okay? But not only that, but the successive distance between each oscillation is getting smaller, okay? So you can see there's a peak here, then there's a peak here. The next peak is slightly closer. Next peak is closer again. Next peak is, you know, the frequency of whatever this is going up until all of a sudden it just shuts off, okay? So the frequency and the amplitude grow, and then it just dies, and it's back to noise. Now, in and of itself, if this happened, you would say, okay, it's just a bit of this weird noise feature, whatever it is, we don't really know. But what's really remarkable about this is if you look at what came into the instrument 1,000 kilometers away and around about 10 milliseconds later, okay, and 10 milliseconds is around about the travel time that light takes to get from one detector to the other, or in fact, a gravitational wave takes to get from one detector to the other. Then what you can see here is in blue is the data in Livingston. In red is the same data that was in red in the top left plot. Now we've shifted it by 10 milliseconds. We've inverted it for technical reasons to do with the orientation of our detectors. But what you can see is on the left, you just get noise. Okay, so the signals don't match up at all. They look nothing alike, which is exactly what you would expect when you just have noise. But then at the same time as the red one starts to get these really coherent oscillations, so does the blue one. And the blue one has the same beautiful correlation, the same amplitude growth, the same frequency getting higher, the higher frequency, shorter distance between the successive peaks. And not only that, it then shuts off at exactly the same time. Now, this in and of itself, this would be Nobel Prize worthy winning. And in fact, it did win a Nobel Prize for basically these two plots here. But what's really exciting about this is the two bottom panels are what people like myself had been touring around the world talking about. We will see something like this when the LIGO detectors start working. You know, so what we're showing on the bottom graphs here are the predictions that you make when you have a 36 solar mass black hole merge with a 29 solar mass black hole, or in other words, this is the prediction that you get from that simulation that I showed you on my first slide. Okay, that movie of two black holes, 1 billion light years away, 36 solar masses, 29 solar masses, you predict that the gravitational waveform should look like this. And once you take out the noise, these two things match up absolutely beautifully. Okay, so this is indeed a Nobel Prize winning winning thing. I'll get to that in a sec, and I'll sort of talk about that in a second. But this is exactly that merger of the first ever observation of two black holes from the using gravitational waves. So in fact, it was the first time we had ever detected gravitational waves, and not only that, it was the first time we had ever directly observed black holes. Okay, so we knew black holes existed. We had lots of different evidence that black holes existed, and there's a beautiful there's a Nobel Prize that was won, I think 2 or 3 years ago. Andrea Ghez was one of them, and she had observations of the galactic center and stars in the galactic center that showed there has to be a black hole there. But we call that an indirect observation because you're actually inferring the existence of the black hole, whereas here we're actually directly looking at the black holes, looking in quotation marks, because we're detecting the gravitational waves that come from them. Okay, how does this all work? I showed you a huge 4-kilometer long instrument. It's this thing over, near Uluru, but that's not where it is, but in the States. How does it actually work? Well, I'm part of the School of Physics and Astronomy at Monash University. We went to our head of school and we said, can we have some money to build a detector like this? He said, sure. How much do you need? And we said, $500 million. And he said, no way. And he gave us a pile of Lego. And he said, build yourself a gravitational wave detector out of Lego. So unfortunately, this is what we had to do. So we built a replica gravitational wave out of Lego. I'll admit that this was a late night when we did it. But it works really well. So let me talk you through exactly how LIGO works. This is a replica. You can see there's a laser here on the bottom left. This is a very, very high-powered laser. The laser shines into these optical cavities, and it hits what's called a half-silvered mirror, which splits the laser light in two. So half of the laser light comes down one of the arms, and the other half of the laser light goes down the other arm perpendicular. And what happens is the laser light comes down the other arm. This is where those 4-kilometer long arms are. There are huge mirrors at either end. So this is a 40-kilogram mirror. So the laser light goes down this vacuum tunnel, hits the 40-kilogram mirror. The light bounces back and it recombines with the light that's traveled down the other arm, recombines at this half-silvered mirror and comes out and is detected in a photodiode. So basically, we detect the phase of the light. Now, what happens when a gravitational wave passes through? The gravitational wave detector actually moves, but it moves in a really, really interesting and characteristic way that allows us to measure the gravitational waves. So what you can see here is that it's actually the length of the arms that is physically changing when a gravitational wave passes through. So a gravitational wave in this case is passing into your screen, and it's causing this vertical arm to extend and shrink in cycles. Likewise, it's causing the horizontal arm to extend and shrink in cycles. But what's really nice about this is that they're exactly out of phase. So when this vertical arm extends, the horizontal arm shrinks. And so what that means is that the laser light that goes into this cavity, the laser light that goes up the vertical arm, if that's been extended, it will take longer to travel up the arm and bounce back than the light that's traveled down the horizontal arm. And so when the light recombines, you measure the change in distance that these two, the two laser segments have gone down, the two paths have taken. So this is how we measure that change in distance. What it really is it's a physical change, a physical stretching of the space in the gravitational wave detector. So this is beautiful. I mean, this is exactly how we detect gravitational waves. Now, you're probably looking at this saying, it took you 99 years to detect these gravitational waves, but the oscillations that I'm seeing here look huge. So here's where that maths come in. Let's actually talk about how big these gravitational waves are. So what I want to do is I'm going to tell you about a quantity called delta L over L. And this is this thing called strain. It's very easy to understand, and let me walk you through it. So the L that's on the bottom of this fraction, it's on the denominator, it's on the bottom of this fraction, that's just the overall length of the arm, okay? So if my LIGO arm, in this case, in proper LIGO, it's 4 kilometers. That's the length of the 4 kilometers that I mentioned. But this Lego LIGO, okay, it's, I don't know what that is, let's say 15 LIGO bricks, 15 Lego bricks, sorry. It's always a tongue twister doing this. It's 15 Lego bricks. So each one of these little bricks is 1 unit of length, and L is 15 of those. Delta L is the amount it changes when a gravitational wave passes through. Okay, so in this case, you can see that my gravitational wave that I've mocked up by just using a stock photography, this is, say, 4 bricks. Okay, actually, let's use a round number. Let's call it 5 bricks. It's changing by five Lego bricks. So in other words, for this gravitational wave that's passing into my Lego LIGO, delta L on L would be 5 divided by 15, or in other words, it would be about 1/3. Okay, so if this number is 1/3, that should be easy to measure. We shouldn't have any problems. Obviously, it's not. It did take us 99 years to build these experiments and actually measure this effect. So how big is this number in terms of the measurements that we actually made? Well, let me put it up. It's this. Now, please don't count the zeros in that, because I just sort of typed them out and I'm not sure if it's right. There should be 21 zeros here. This number is 10 to the minus 21. It's a really, really small number. Okay, it's a really small number, and it's a hard number to get your head around. So let me try and help you get your head around it. What you can do is you can ask the question, if I went back to my school, my head of school, and I said, okay, we want to build a detector like this made out of Lego, but so that it can actually detect a gravitational wave. In other words, I want to change L such that when a gravitational wave passes through, delta L is 1 block. Okay, and if I can do that, I can build L to be long enough, and I've given away the punchline accidentally here. It's supposed to be a question mark over that first one. No. Anyway, I can make L long enough that my gravitational wave passes through, and this changes by 1 block. Now, it turns out I have to build my Lego LIGO to be 500 light years long. Mm-hmm. To put that in context, the distance between the Earth and the Sun is 8 light minutes. The distance between the Earth and the next nearest sun, or the next nearest star, Alpha Centauri, is 4 light years. So in other words, I have to go a lot further. I have to go another factor of 100 past the next sun, the next star away from our solar system. If you know anything about sort of the galaxy and things along those lines, this takes you out to around about the distance of Sagittarius A star, which is the supermassive black hole in the center of our galaxy. So I have to build my Lego LIGO to be as big as our galaxy, or about half as big as our galaxy, to be able to detect 1 change in a Lego block when this gravitational wave passes through. If that's a mind-blowing number, let me put it in another way. The distance, when this gravitational wave passed between us and the Earth, the distance between us and the Earth, we're on the Earth. When the gravitational wave passed between us and the sun, or when it came through our solar system, the distance between us and the sun changed by less than the width of a human hair. Okay, so, and that's what we measured. That is the distance change that we measured using this Lego LIGO. In LIGO proper, the 4-kilometer arms, they changed by 1/1000th the size of a proton. And that's what we measured. Okay, this is I'm trying to instill in you how small this number is. Yeah. It's whoppingly small. All right. So that's what we did. Now, that's why, if I go back to this graph now, that's why you can see this strain number on the axis, on the vertical axis. This is what we were talking about before. This is 10 to the minus 21. This is that delta L divided by L. And you can see it's just noise down here. And then when the signal comes through, it gets up to around about 1 by 10 to the minus 21. Incredibly small amount. Now, what's really beautiful and what's really truly remarkable about this is that we can use these little wiggles in our gravitational wave detector, not just to say that something happened in the universe and we don't know what it is, but in fact, we can tell you that the masses of the 2 black holes were 36 times the mass of our sun and 29 times the mass of our sun. And actually, I have a more precise statement about that. And this is actually the probability of those masses. And I'm not going to walk you through this in too much detail. But what I can tell you is that the more massive black hole had a mass of about 36 solar masses, so 36 times the mass of our sun, plus or minus around about 4 solar masses. The secondary object had a mass of about 29 times the mass of our sun, plus or minus around about 4 times the mass of our sun. And you can see this is the probability distribution of those masses. You can see that it's degenerate in this space, but I'm not going to go into any details here. This is sort of very getting into the technical science that we actually do. But if anyone's interested, I'm happy to talk about it. This is actually one of the core things that we do at Monash. And my group over the last number of years has been building the software that turns these wiggles into the statements about the science. You know, what do you learn about the science by learning about what the masses are. You can learn about how these things formed. You can learn about how far away they are. So I told you initially that these two black holes merged around about 1 billion light years away, or 1 billion light years ago. That was a little bit of a lie. So let me tell you the truth. It was around about between 1 billion light years and 2 billion light years. And we don't actually know the distance to within that factor of 100%. And the reason that we don't know that distance to within a factor of 100% is it turns out that these systems, if the binary system is face on to us, so in other words, if you can see my camera, it's sort of orbiting face on compared to orbiting side on, like that. If it's orbiting face on, then we think the system is a lot further away because the gravitational waves that come out are louder. Okay, they have a higher amplitude. And so if it's edge on, we think it's a lot closer. And so we end up with this degeneracy. And that's what you can see in this plot, that we actually don't know whether this system was a long way away, 2 billion light years away, but but face on, or whether it was a lot closer, but edge on. And we don't know. Okay. But this is the best that we can do with the signal that we get. The other thing that we can do with this one detection, and this is going to become relevant very shortly, is we can say approximately where on the sky it came from. And the way we do that is we have 2 detectors. In this case, we have 2 detectors. The signal comes into one of them, 10 milliseconds comes in, it hits the other one. So we can use that to triangulate a little bit on the sky where it came from. Now, we also have a little bit more information because we have what's called the polarization. We have the angle of the 2 detectors and various technicalities like that. And what this tells us is actually that it came from somewhere on the sky, which is actually a whoppingly big patch of sky. So this is what we call a sky map. This is the probability distribution of where on the sky it came from. And it's unfortunately really big. You know, if you compare this to the size of the moon, this is many, many, many moons, for example. And this is a problem because if you have what we want to do with these signals is we want to say a signal just went off. It went off in that region of the sky. Let's take all of the telescopes and point them in that direction and see if we can see some light that comes from the same signal, light, radio waves, X-rays, gamma rays, something like that. Okay. And if you can, then great. And I will talk about that in just a second. Unfortunately, with a signal like this, the sky area is so big that the telescopes have to sort of tile over that sky, and it becomes really difficult. I can see there's a couple of questions in the chat. I'll very quickly.
Yeah, I'll just pass them on to you. So one question was, how many black holes do you detect? Was it just that one, or are they now thick on the ground?
Yeah, so they're becoming thick on the ground now. So this first one was in the 14th of September 2015. In what we called the first observing run, and I was going to talk about this a little bit later, but I can mention it now. We detected I think it was 4 binary black hole systems. We then switched the instruments off, upgraded them, turned them back on about a year later. We detected another 10 systems. I'll talk in a second about one of them. It was very special. We switched it off, turned it back on again, and now we have 90, depending on how you count. There are some which are a bit suspect. We quantify how suspect they are. But so we've got around about 90 now. The detectors are off again. They've been off since around about mid-2020, and they're going to go on again in March of next year with increased sensitivity again. And we're going to start detecting them, we predict, at around about 1 every 1 or 2 days. So we've gone from rags to riches in terms of, I still remember the hard old days where we'd build pipelines, software pipelines to analyze the data that just didn't exist. Now we have far too much data that we don't know what to do with it. So
talking about the precision of your of the instrument, that it sounds like it's much shorter than the wavelength of light. So what is the wavelength of light you're using in the machine, and how do you detect things that are even smaller than those waves that are interfering with each other?
Yeah, so that's a good question. So the wavelength of light that we're using is 740 nanometers, I believe. It's just out of the optical spectrum. So it's just out of optical.
A lot bigger than a proton.
Yes. Yeah. So what you have to do is you have to bounce the light multiple times in the detector to accumulate this signal and noise. And in fact, I'm not sure, I can't remember how I presented this, but I might have misspoke, because we often talk about, we measure the change in distance, but what we actually measure is we measure the change in the light travel time. So we're measuring it. It does matter what the wavelength of the light is, but it matters less because we're measuring the we're measuring the amount of time it takes the light to travel through that interferometer, if that makes sense.
And now here's a nice one for you from Bob Aikenhead. What particle is associated with gravitational waves?
Interesting. Gravitons. So if you're a particle physicist, you would never talk about curvature of space-time in the way that I'm talking about curvature of space-time. You would instead talk about gravitons. And the way any gravitational interaction happens is through the interchange of gravitons. Just like electromagnetic interactions happen by the interaction of photons and various particles like that, and there's gluons and all of these kinds of other things. So these are gravitons. Now, it conceptually gets a little bit harder to think about gravitational waves being just gravitons, because if I just have a ball of mass sitting there, that is also emitting gravitons in the sense that that's a gravitating object. So it's interacting with other gravitating objects through the interchange of gravitons. So that also happens when I have gravitational waves, but it's not like there's a sort of special entity there. But certainly you can rederive all of the equations of gravitational wave either from a geometric perspective or by thinking about those particles, gravitons.
And one more question while we're interrupting you. Why 4 kilometers long? Is that a magic number, or is that when the money ran out?
Yeah. There's so much truth to that second comment. So it's not a magic number. The magic number would be 16 kilometers for various reasons. But the longer the better. Having said that, costs do increase almost linearly with the length, but you also start running into a lot of other troubles. Even just things like the curvature of the Earth becomes a really big problem. So is 4 kilometers is not a magical number at all. Now, the next generation of observatories that people are talking about building, there's one in Europe, which is called Einstein Telescope, and that's proposed to be 10 kilometers and fully underground. There's one in the US, which is proposed to be Cosmic Explorer, it's called, and that's going to be 40 kilometers. Now, when you're out at 40 kilometers, you have to seriously think about the curvature of the Earth. And what that means is you have to also dig down, because you don't want to put the end stations on stilts, because that'll introduce seismic noise. So instead, you have to sort of dig down. And that digging, we've just gone through this exercise of costing that up in Australia, and it's expensive. It gets expensive. So I've got a hybrid proposal, which doesn't cost anywhere near that much money, which I'll get into towards the end. But yeah, so that's 4 kilometers is not magic, but it does come with a lot of serious thought that's gone into it. Now I can actually see there's one more question that I'm gonna go with as well. That would a third installation allow for more accurate locational? And the answer is yes. The answer is absolutely 100% yes. So what I told you up until this point is all about the 2 LIGO detectors. While they were being operated in this sense, another detector was being built in Italy. and it's just outside of Pisa, where, of course, there's a more famous leaning tower, but there's also a gravitational wave observatory. Now, let me skip over that. If I fast forward, in fact, let's fast forward to August 2017, and I'll sort of get to this figure in a minute. We were into our second observing run. So LIGO had detected some 7 or 8, I think, binary black hole systems, just like the first one. And it was still going. And early in August, this third observatory switched on, and the third observatory was called Virgo in Italy. And it's not quite as sensitive for various technical reasons. It's only 3 kilometers. It's got some different technology and things along those lines, but it was just starting to switch on. And on the 14th of August in 2017, another black hole binary system, very much similar to the first one, came into the system, and we detected it with all 3 detectors. And so what that meant is, instead of having 1,000 square degrees on the sky for the sky localization, we had about 60. Okay, for the reasons that Malcolm mentions in the chat, it allows for that greater sky location. You're now doing triangulation, not with 2 detectors, but with 3. So you can break the degeneracies in the sky with the timing of when the system comes in. So this was absolutely gorgeous. This was this first observation with this Virgo detector. Everyone that had been working on that was celebrating very, very hard. They had exactly 2.5 days to celebrate, and then we got something even more exciting, and they had to stop celebrating that and work even harder. So that's what I want to tell you about now. We're fast forwarding now, not to the 14th of August 2017, but the 17th of August 2017. And on the 17th of August 2017, this happened. What I'm showing you on the bottom left here is the gravitational wave signal. What we're looking at now is not just the time series that we were looking at before. It still is the time on the horizontal axis, but on the vertical axis is the frequency. It's the gravitational wave frequency. The parts in blue are just noise. We don't care about that. But what you can see is there's this beautiful curve that goes through here, which is this signal that I was talking about earlier when I talked about that the successive peaks between our gravitational wave signal get closer and closer and closer. Well, that's the frequency of the gravitational wave signal going up. So that's what you can see here. The frequency of the gravitational wave signal, it starts off low and it goes up. And in fact, these frequencies are actually in the audio band. These frequencies are frequencies that you could, if you convert it to a sound signal, you could actually hear. And so I can see Elizabeth Fingal has asked, what do you mean by louder? In fact, that's what I really do mean by louder. The signal, if it was light, you would call it brighter. But because these are waves that are actually, the frequency is in the audio band, we actually call it louder. And so a signal like this makes a very characteristic sound, which is what we call a chirp. And it just starts off low and it gets higher, and it chirps up. So this is a remarkable signal. And the reason it's remarkable is you have to look on this horizontal axis, this time axis. And if you remember back to the first one I showed of these, it was not over 10 seconds like this one is, but it was over 200 milliseconds. So this signal is actually a lot longer. And actually, if you extend this out, it actually went for around about 60 to 90 seconds, depending on how you count. Now, why would something take so much longer to merge? The reason is these things are a lot smaller, okay? So whereas before I had these really big black holes, they were 30 times the mass of our sun. Now I have these really small objects. They're really compact. And what that means is they can orbit each other and get much closer to one another before they finally merge. So they merge at a higher frequency because the orbit's getting closer and closer and closer together. So in and of itself, that's interesting. That's great. This would have been the first thing that we had seen that had such a long signal. But the truly remarkable part comes next. What these are plots showing showing gamma rays from two different satellites, but 3 different instruments. So what I have here is the Integral spacecraft and the Fermi spacecraft, which has 2 instruments on it, both called GBM, which stands for Gamma Ray Burst Monitor, and they look in different bands. So they look at different energy gamma rays. And what you can see is on the left, these just show noise. Okay, so this is the number of photons that they're collecting at any given time, or in other words, the amount of light that they're collecting at any given time. And the red line just shows you what they normally detect when they're just looking out into empty space. Okay, so they normally just detect a background. It's noisy. This is what it looks like. All three detectors, all the same. You can see that around about 1.5 seconds after this gravitational wave merger, all three of these actually detected an excess, a significant excess of gamma rays. And this is something that we typically see. We've seen lots of these. These are called gamma ray bursts. Okay, and this is actually, you know, we understand a little bit about the physics of these, and I'll sort of talk about that a little bit as we go. So this was the first time that we had ever seen a gravitational wave signal, and from exactly the same source, we saw these gamma ray signals. Now, we know that because the gravitational wave signal, because it was detected with all three detectors, we could pinpoint it to within about 30 degrees on the sky. And the gamma ray burst detectors said, oh, this is actually coming from that same patch of sky. Again, in and of itself, this would have been beautiful and truly remarkable, but the story certainly doesn't end there. There we go. So this is an image of a very random galaxy. It has a very boring name. It's called NGC 4993 because there's nothing particularly interesting about the galaxy. And this is an image that was taken with the Hubble Space Telescope on the 28th of April, 2017. So in other words, this was a handful of months prior to this gravitational wave detection that we're talking about. Now, the image on the right is remarkable because it has a giant whopping big red arrow on it, which always helps us astronomers to understand what's there. But the beautiful thing is this is the same image of the same galaxy, not taken with the Hubble Space Telescope, but taken with a 1-meter telescope in Chile, in the mountains up in Chile. And it's taken on the same day, August 17, the same day that we saw this gravitational wave event. In fact, it's taken 11 hours later. And the whopping big red arrow is pointing to a dot that was not previously there 3 months ago or 4 months ago. Okay, all of the other dots on this, you can line up between the two images and they're the same. They're stars in the local universe, for example. This one on the right, that one there would be a star. There might be more distant galaxies, a few of them, things along those lines. But this thing is absolutely not there previously. This is new, okay? How do you get something so bright and so new? You have to merge two objects together in a cataclysmic collision that emits not just these gravitational waves, but it emits a lot of light. So now this is the movie that is not going to work. You know what I'm going to do? Because I think it's really beautiful to be able to show this if I can. Here we go. All right, let me pause this. What I'm showing you now is an image. This is an image of the same galaxy, but it's taken, you can see this initial image is taken some 1,000 days earlier. So T minus 1,000 days. This is a 12-year-old image. It doesn't really matter. It's not important. But when I run this video, it's going to show an image of this galaxy from that 11-hour period after the merger through a whole series of days. And on the right is what we're going to show the spectrum of this new point. So let's, for the first time through, let's ignore the thing on the right and let's all just focus on a point up in the top left, around about where my cursor is. Okay. So you can see as this starts there, and it starts off beautifully blue. And in fact, as it fades, it turns really red. Okay, and then it keeps fading. You can see we're 7 days post-merger now, 8 days, 9 days, and it's really faded, okay? 11 days, it's really getting hard to see, okay? So what we're seeing on the right, I'll play it again in just a sec. What we're seeing on the right is the spectrum of this. And what you can see, well, you can see it here. Initially, it started off really short wavelength, okay, but really bright. There's a lot of photons being collected. And then as that signal decayed, you can see actually the spectrum changed. I'll play it one more time just so we can see. It's really just quite beautiful over this 11 or 12 day period, how this thing changes color, goes from blue to a bit purple. There are various peaks in this spectrum, which chemists and nuclear physicists would absolutely love to see. And I'll talk a little bit about that in just a second. But you can see that this thing fades and eventually becomes really red and becomes too hard to see. All right, let me go back into my full presentation. Let's actually fast forward to another movie. So I haven't told you what this thing was yet. What creates something like that? Because when we talked about the first detection, that was two black holes. Two black holes, when they merge, they start off black, which means that they don't emit any light. Then they merge, they're still black, which means that they don't emit any light. It's incredibly boring. A signal like this, okay, I'm going to mute this because it's a signal like this has to come from something that's not black holes. So what are they? These are two neutron stars that collided with one another. A neutron star is a dead stellar remnant. So it's not like our sun, but consider a star that's a bit bigger than our sun. It goes through its whole life of burning nuclear fuel, shining for 100 million years, eventually explodes in a supernova and collapses back in on itself. And it forms what's called a neutron star, which is around about the mass of our sun, probably about 1.5 times the mass of our sun, but it's squeezed into a size of around about 10 or 20 kilometers. So in other words, it's as big as the Melbourne CBD, but it has the mass of our sun. Truly remarkable objects. And in fact, this was two of those objects orbiting one another, which is where we saw the gravitational waves, colliding, and that's where we see all of these different gamma rays, X-rays, optical, radio, all of these kinds of things. So let me play a movie for you. We'll see how the volume goes. That's not too bad. So this is all artistic impression. Two neutron stars spiraling in to one another, getting closer because they're emitting gravitational waves. And then it crescendos. I'll just let it play. All right. And then some advertising from NASA. Let me rewind. So, okay, what you could see there was these two neutron stars. They go round and round and round and round and round together. They collide, and then out of the poles of this collision comes these humongous jets. Okay, and those humongous jets plow into what's called the interstellar medium. So there's this gas and dust, which is really sparse, but it's enough to slow down this jet, heat up the jet, and it emits those gamma rays. So it has this shock for the surface, emits gamma rays, and that's what we detect. So we know it takes now 1.5 seconds for that jet to get launched, the jet to come out, shock with the interstellar medium, and then launch emit gamma rays that then come to our detectors. It launches all of this. There's all of this other ejector material, okay, and you can see around in the middle here. This is where matter would have got flung off during the merger in this really violent collision. And in fact, what happens during this part of the merger, or during this stage, all this matter actually goes through nuclear reactions, and you end up creating lots of really, really heavy elements. And these heavy elements are called things like lactonides and actinides, okay? And they really quickly decay through a process called R process, nucleosynthesis, all just jargon at this point. But what's really important about that is this decay of these heavy elements is what we saw in that spectrum that went from really, really red, faded to purple, faded to blue. That's the decay of these heavy elements. And what's beautifully exciting about that, if I can move on to my next slide, what's really exciting about that is you can look at the table of elements in our universe, and you can actually say, well, a huge fraction of these elements actually get created in neutron star collisions, just like this one that we had there. Now, so this is a table of the elements, but it's a table of the elements that's color-coded by where these elements get created. So for example, hydrogen and helium are really blue in this because they all get created in the Big Bang. Okay, Big Bang fusion happens. Hydrogen gets created, almost all of the hydrogen in the universe gets created in the Big Bang. Almost all of the helium in the universe gets created in the Big Bang, some of the lithium. And as you go through, you can look at anything that's here that's purple gets created in neutron star collision. So you can see it's those heavier elements, but it is things like gold. It is things like silver. Okay, so you've got silver here, you've got gold, you've got lots of these really heavy elements. And so in fact, if you've got a wedding ring on, I don't have mine on today because I've got a partially broken thumb. That's a whole nother story. But, you know, if you look at your wedding ring, if you look at the gold that's in the chips in your phone, all those kinds of things, they were created, that gold was created in a neutron star collision probably 1 billion years ago, but then it evolved throughout the universe and ended up settling here on Earth. So this is, you know, this is an incredible way to learn about all of these sort of the way these heavy elements get created. Just for some reference, the lactonides and anthonides that I was talking about are these heavy elements that are in this sort of bottom row. There's a lot more of them, but they sort of decay. Those are the ones that get created and then decay really quickly because they're not stable. They're up sort of past an ion stability threshold. So this is what got created in that event. We're still observing that event today. We can still see it very faintly in radio observations and some X-ray observations as well. And we can still learn a lot about it, and we are still learning about it. I'll mention, so this was sort of spoken about a little bit before. We discussed that we now have 90 detections of gravitational waves. And this is a beautiful image that's called Masses in the Stellar Graveyard. The horizontal axis here, so is just when we detected things. So we detected our first one. This is that first signal that we ever detected on the left. And it goes the whole way through to the last one we detected. And the vertical axis shows the masses of these objects. So you can see two black holes merged to create a much heavier black hole. Okay. And that's how we read this. And so what you can see is most of the signals that we're getting are these 30 solar mass black hole mergers, but we are getting the occasional, this first one down here, that is our 170817, that is this first neutron star merger that we observed that I was just talking about now. And there's this whole series of observations, which I could talk about in a whole bunch of detail. I could talk about the special ones in this, and I've got a whole bunch of slides that do go into those details, but instead, I think it's worth sort of pausing. I can see that there's a question in the chat about a space-based gravitational wave detector. So I'll take that and then I guess open it up for other questions. So the space-based gravitational wave detectors is a fascinating one. The answer is yes. There are plans for a space-based gravitational wave detector. And not only that, it's funded and it's due for launch in 2032. And this is something that's called LISA, stands for Laser Interferometer Space-Based Antenna. And what it does is, instead of having arms that are 4 kilometers long, we have arms that are 1 million kilometers long. And so obviously they're not arms at that level. They're then 3 separate spacecraft that they trail the Earth's orbit by some 20 degrees. So they're in the same orbit as Earth, but just offset. And they're separated by 1 million kilometers, and they shoot laser beams between each spacecraft and measure the change in distance between each of the craft. Now, what this does is it actually doesn't measure gravitational waves from objects like this, but instead it measures them at lower frequencies. And so instead of being at 100 hertz or 1,000 hertz, it measures them at microhertz, or it's sort of 10 to the minus 4, 10 to the minus 3 hertz. And there we actually, instead of measuring black holes that are 10 times the mass of our sun or 30 times the mass of our sun, we hope to be able to measure black holes that are 10,000 times the mass of our sun or 1 million times the mass of our sun. And we know that these exist. We've never seen any merge, but we have every reason to suspect that they do, and I can back that up with very solid astrophysics statements. But that gravitational wave detector will detect those things and a lot more other things as well. It's worth saying that the Chinese are also building an instrument. They've got 2 proposals, and it'll get downgraded to 1, or descoped to 1. One of them is called Tianqin, and it's going to be very similar to LISA as well. And there's in a sense a very healthy space race going on between the LISA consortium and the Chinese in that way. So yeah, there are plans to build one of those, and it's super exciting stuff.
It seems counterintuitive that you need the bigger space machine with the bigger arms to detect larger masses.
Yeah, and it does in a sense. Yeah, you're right. And the reason is because of that. When a black hole is bigger, it's more elongated. And if it's more elongated, then when 2 of them merge, they merge when the separations of the middle of them is further apart. And so the frequency of the gravitational wave is much lower.
Yeah.
Okay. And so that's sort of the key to it is it's that gravitational wave frequency. Now, if you want to get lower than around about 10 hertz on Earth, you really can't, because we're limited by seismic noise. There's this seismic wall that would just kill us. I mean, just for some context, the gravitational wave detector in Livingston is a couple of 100 kilometers away from the beach. But you can measure the waves. When a big wave comes in, you can measure it. You see it. It's noise. It's a problem. You know, these kinds of seismic activities, seismic noise, just the shifting of the ground. You know, it doesn't even have to be a truck. When a truck passes by, it's just anything. The constant shifting of the ground is a problem. So to get down to those lower frequencies, you've got to go up into space. There's also a proposal to go to the moon, for what it's worth, and build one on the moon, which I think is a really beautiful and interesting idea.
And these detectors are orbiting the sun, not orbiting the Earth. Is that?
That's right. Yeah, that's right. And that's simply because it's easier to keep them in, to keep them synchronously that far apart from each other. So that's just sort of some, yeah. I can see another question in the chat. Why are neutron star collisions detections much less frequent? And this is a really interesting question. The answer is because they're not necessarily less frequent in the universe. It's just that we can't see them as well. And so we have to wait for them to happen much closer to us than the other ones. So to give you some context, I mentioned that the first black hole merger happened at around about 1 billion to 2 billion light years away. The first neutron star merger happened at around about 140 million light years. So it's almost a factor of 10 closer. And it was a similar sort of loudness in our detector, a similar signal to noise ratio is the technical description. And the reason for that is just because they're lower mass. So you have less mass, which means it's a less violent collision in terms of the gravitational wave, which means that we can't see them out as far. So even though they might happen at a similar rate throughout the universe, we just can't see as far into the universe with the neutron stars as we could with the black holes. How are we going for time, David? Well,
It's just on 7:30, so
yep.
It's up to you. Well, I'm certainly just absolutely enthralled. So I'd like you to go on all night if you could. But I know that there's your cat that probably needs to be fed or something.
No,
so I'll leave it up to you. But
I don't know what.
I'll invite people to remind people to put questions in the chat box if they've got them.
Let me spend a few minutes giving a pitch for some money, because in case anyone out there has a spare $100 million or so, you know, it's always, you got to get the sales pitch in at the end of the talk. So we've talked about the difference between trying to measure supermassive black holes with a low frequency and a detector that you would therefore send out into space. The other thing that we've talked about is that we measure these neutron star mergers, and they merge at a really high frequency. Now, it actually turns out with this first neutron star merger that we saw, we didn't actually see the merger. We only saw the in-spiral. So we saw these two objects spiraling in. They were traveling at some whopping speed, something like 0.6 or 0.7 the speed of light. And then just before they merged, we lost them. And the reason we lost them is our detectors are not sensitive enough at the high frequencies that you need to detect the gravitational waves from a neutron star merger. So we missed out on a whole bunch of physics, but not only that, when these two neutron stars merge, we then don't know what happens next. We suspect, and we have reason to believe, that another neutron star survives the collision. It's quite massive. It might be about 2 times the mass of our sun, maybe 2.5. We don't know, because a lot of mass gets thrown off during the collision. And eventually, so that will survive for some period of time. It will be the hottest object in the universe by orders of magnitude, something like 10 to the 10 Kelvin, 10 to the 11 Kelvin. So in other words, 11 orders of magnitude hotter than what we are on Earth. It'll be the densest object in the universe at the given time. It'll be something like 15, maybe 16 orders of magnitude more dense than water or than anything on Earth. It'll have the strongest magnetic field in the universe, some 15 orders of magnitude stronger than what we can create on Earth. And this thing will survive for some period of time, and then it will eventually collapse to form a black hole. We don't know if that happens in 10 milliseconds. We don't know if it happens in 1 second. We don't know if it happens in 100 seconds or even a year. We don't know these things because we can't observe them with gravitational waves. So we have a proposal to build a gravitational wave observatory that would target those systems and a lot more, but really target those systems to learn about the physics and the astrophysics in these most extreme regions of the universe that we have no other way of really learning about. The proposal is something called NEMO. And what it is, so NEMO stands for Neutron Star Extreme Matter Observatory, but really we just like the play on the language associated with the Pixar movies, and we want to have a project called Building Nemo, and we want to have a project called Funding Nemo, and all in the spirit of Finding Nemo, the movie. But we think we can build this. We've done a lot of costing estimates for this, and we think we can build it for around about $100 million. Australia is one of the perfect places to build it because we have land. That land is seismically very, very quiet, and we have expertise. And so we know how to do this. We just need, we need the funding. We need to go through all of those different kinds of exercises. So I have a whole bunch of sort of technical slides here that talk about the details of all of this. But really, the science case for doing this that we're working on really solidly at the moment is for these binary neutron star mergers and trying to measure what we call the equation of state, measure how nuclear physics works in a place in the universe where we have no other way of measuring it. And so that can inform our understanding of gravity. It can inform our understanding of nuclear physics. And we just don't know what kind of technology we're going to end up developing from those kinds of discoveries. At the same time, this instrument would serve as a technology driver for those instruments that I was talking about before, Cosmic Explorer and Einstein Telescope. So we have science cases around binary neutron star mergers. We think you'd be able to detect supernovae. Supernova is the deaths of massive stars. When they collapse in on themselves, and then they undergo this core bounce. And so the matter all gets really squeezed up small, and then it bounces back out. And that's when you see this huge explosion. When that bounce happens, the gravitational waves that are expected to get created are high frequency and should be in that band where we'd expect to see these kinds of things. And there's a whole bunch of other sort of science cases. We expect to see what we call mountains on neutron stars. And a mountain on a neutron star is that I have a single neutron star. It's rotating just like an Australian rules football would rotate. If that Australian rules football was rotating, it would emit gravitational waves because it's asymmetric, it's not symmetric, so it emits these gravitational waves. But the beautiful thing about neutron stars is we know that they are spherical to 1 part in about 10 to the 8. Or in other words, if I have a 10-kilometer neutron star, they are the biggest mountain on that neutron star is less than a centimeter tall. Okay. We don't know how asymmetrical they are, but we expect that we would be able to actually observe gravitational waves from those. And again, because of how fast these neutron stars rotate, they should be in a region where we would see them with this proposed detector. Lots of other burst sources, but of course, cliche alert, opening a new window on the universe, which is this picture here. Anytime you start looking at a new band of anything, just like every time we started, when we started looking at gamma rays, pointed gamma ray observatories to the sky, we started to understand how supernova work. We started to understand gamma ray bursts, neutron star mergers. When we started looking at the sun in radio, we started understanding how the sun actually works, hot and cold patches, all of these kinds of things. So there's all of these kinds of things that we don't know what we would find, which is the exciting part. It's the unknown unknowns that, we would hope to be able to discover. You don't need to see preliminary designs, but scoping study tells us that it would cost us on the order of $100 million to build such a center. We have site locations. We have around about 6 locations where we think we could build this in Australia for relatively cheap. If you go too far out, it becomes more expensive. If you go too close to cities, it becomes more expensive, all of these kinds of things. But we know we can do this. So anyway, that's my very quick elevator sales pitch. If anyone in the audience has a spare $100 million, we could change the name and name it after you. We're happy to sell our souls to the devil and things along those lines. But yeah, no, on a serious note, I think this is a really exciting space. This is a really exciting future project that has some really interesting science goals and technology development that we can try and drive and try and lead out of Australia. And it's a really exciting thing that we're hoping to be driving in the not too distant future. So keep your eyes out for that.
1% of the cost of a submarine.
Look, I've brought that up a few times. Yes. yes, we could sacrifice less than one submarine and go a long way.
So that was an absolutely stunning talk, and I'll invite people to put questions in the chat function, and you can see that too, can't you?
Yeah, I can see that. Yeah.
So address them.
So I can see that is it Francis has a question. What's the difference between a graviton and a photon? So a photon, so in some sense they're similar, and in some sense they're vastly different. A photon is a photon is light. So when we observe light, the light that's coming into our eyes, that is photons. They are oscillating waves of electric and magnetic fields, technically, but that is the light that we see. In the same way, it's also the microwaves that we use in our microwave oven. They are the radio waves that we collect in our radio dishes when we, all of these kinds of things. They're X-rays, they're gamma rays. These are photons. So they are oscillating electric and magnetic fields. Gravitons are not. They have nothing to do with electric and magnetic fields, but instead they have to do with the gravitational field. So they are, in a sense, oscillations of gravity, but they're a particle description of gravity, if that makes sense.
Well, I think,
yeah.
Oh, well, I was going to wrap things up, because, but if you've got another question you're going to answer. No.
Yeah, actually, I just saw Malcolm's question is really interesting. So let me give that a brief one, because it is, aren't millisecond pulsars also being proposed as useful as space-based equivalent? And they have unique but precise timing. Absolutely. And this is a really beautiful space. So, and this is being, in some sense, led out of Australia, but there's collaborations around the world as well. So we time millisecond pulsar. So a millisecond pulsar is a neutron star that spins every millisecond incredibly regularly. And so because they're massive, because they've got this, really regular spin, if you time how often they spin, you can use them as remarkable clocks. And in fact, their precision rivals that of the best atomic clocks that we have on Earth. So you can use them as, you can use them for navigation, you can use them as timing tools, and you can use them to detect gravitational waves. Because what happens is when a gravitational wave passes between us and the pulsar, the distance changes, and therefore the time of arrival of when that pulse arrives also changes. Now, instead of detecting gravitational waves down at 10 to the minus 3 hertz, like we would with LISA, this is 10 to the minus 9 hertz. So these are really supermassive black holes that we're trying to detect. Supermassive black holes, gravitational waves from the very, very early universe, things along those lines. So yeah, there's ongoing efforts. We haven't detected anything yet, but actually there will be some very interesting things to watch in the coming months in this space. There's potentially some claimed, not going to call them detections, but very good evidence that there may be gravitational waves in the data. When the frequency is 10 to the minus 9 hertz, that translates to around about 1 on a year. In other words, to see one cycle of a gravitational wave, you've got to observe a pulsar for more than a year. And so, in fact, we've been observing them for 10 years, in some cases up to 30 years. And that's how we have to, we have to use all of that data over 10, 20, 30 years to be able to detect gravitational waves. So it's a hard problem. We're working on it. I have a very, very talented PhD student, Rowena Nathan, who is driving some of the effort on that. But yeah, there's a lot of work going on.
And I'm paraphrasing a question from Elizabeth Finkel.
Yes.
Are we ever going to detect a graviton?
Yeah, great question. And I like how you've how you have paraphrased that. So we have never detected a graviton, and I suspect we never will. I'm not an expert on that. What I will say is, when a gravitational wave, for example, passes through our detectors, we talk about that signal being so minute, so weak, 10 to the minus 21 strain, incredibly, incredibly weak. But the problem is the number of gravitons that actually pass through at that time is huge, absolutely humongous. I can't remember the number, but it's something like 10 to the 40 or 10 to the 30, something like that. It's a whoppingly big number, which means that the effect of any one graviton on that gravitational wave signal is completely negligible. And you need that many gravitons to create anything that you can detect. So I think it's true to say, from a particle physics perspective, are we ever going to detect gravitons in that way? I think the answer is no. Again, I'm not an expert, would need to ask particle physicists. We've got some excellent physicists who work on experiments like the LHC at Monash, who would be able to provide much more nuanced answers to this. But my intuition is that the answer is no.
Oh, well, it just remains for me to thank you for an absolutely stunning talk. It's been incredible delight and a great way to finish off the ANZAAS year of science talks.